Hello everyone, it's time to talk about converging lenses. As we talked about last week, converging lens is shaped somewhat like that. It's wider at the middle than it is at the ends, and a lens like this is called a converging lens because it has a focal point on either side, and they're identical, and all light rays that pass through this lens horizontally will exit the lens through the focal point. So you can see wherever they come in horizontally, they'll exit through that focal point. And it would be the same if the light was headed the other way. All the light rays would focus through this focal point. These lenses are symmetrical. They are very thin. They're shown wider here so that you can understand what it's shaped like. And they also are subject to some spherical aberration, just like the mirrors that we've talked about already. So we'll work through one of the On Your Own problems, On Your Own 12.8, to review some of the principles about how you do ray tracings in a converging lens. So first we'll draw the lens, and we'll mark the center of this lens. And then I'm going to draw the optical axis, which would be through the center from top to bottom. So I have to extend my line a little bit here. So for problem On Your Own 12.8, it states we have a converging lens with focal points that are 8 centimeters from the center. So we'll use the ruler and we'll mark 8 centimeters there and 8 centimeters there. And we'll mark them both as focal points. We have an object that is 5.0 centimeters from the center of the lens. We could put this on either side, but I've chosen that side. And we will indicate our object with an arrow. That makes it easy to determine where the light rays are coming in, where they go out, and what the image should look like. So we want to know if we have an eye here, looking at this object through that lens, we want to know what that object is going to look like. And we'll try to answer the same 3 questions that we answer for all of these things. Is it real or virtual? Is it inverted or upright? And is it reduced or magnified? So we begin with our 3 different light rays that we always choose the same 3 light rays, and I recommend that you use 3 different colors to do that so it's clear what's happening. So the first ray that we're going to use follows the principle that all light rays that enter the lens traveling horizontally will exit the lens traveling through the focal point. So that's the first line we're going to draw. So it's going to enter the lens horizontally or parallel to the optical axis. And we would draw that line into the center of the lens. Then it's going to exit the lens through the focal point. In general, I think it's a good idea to go ahead and extrapolate that ray backwards, just because sometimes it's hard to tell where the image is going to form, and that saves you a step later on. The second line that we will draw follows the principle that all light rays that enter the lens traveling through the focal point will exit the lens horizontally. So this is sort of an opposite partner to the first line. So we would draw the light ray coming through the focal point and touching the top of the image. And then that will exit horizontally or parallel to the optical axis. And we'll go ahead and extrapolate that one back as well. Alright, so we have our two rays there. The third ray that we will draw, and this is my favorite because it's the easiest one, is all light rays that enter the lens traveling directly towards the center will experience no deflection as they exit the lens. So this one simply has to touch the top of the image and pass through the center of the lens. Now you can see that all of the actual light rays have diverged out here because of the position of the object. If we extend this light ray back, and this is the actual light ray, it's not extrapolated, we can see that there actually is a point where all of these rays cross each other, and it's right here. So all three of those rays do cross each other. Two of them are extrapolated, one of them is the actual light ray. Since there are extrapolated rays involved here, we would say that this is a virtual image. We'll draw the top of it right there where the beams converge, and the bottom of it will always sit on the axis just like the actual object does. So we can tell from that that it is upright, and we can also see that it appears much larger to this eye than the actual object, so it is magnified. So that is the solution to On Your Own 12.8.